The mole. Now, the mole, oftentimes, when people think of it, they think of the little varmint that digs through the garden. Others may think of a beauty mark they may have, or even a secret spy of some form. But in chemistry, what the mole is simply a really big number. And this really big number is kind of specific. The mole is the number equal to the number of atoms exactly in 12 grams of carbon 12. Now, this definition will be important here in a little bit, but what is this number? Well, this number is 6.02214 times 10 to the 23. Now, this is a really huge number, and it's hard to stress how big of a number this really is, but I'll try to relate this in some manner. And this has been measured in several different ways, and this is often referred to as Avogadro's number. Now, one way we can look at this is we can consider the average amount of heartbeats someone has. It's 80 beats per minute. And if you attain an associate's degree in 2 years, that would be 8.4 times 10 to the 7 heartbeats to obtain that degree. Now, this is nowhere near Avogadro's number. So let's take a look at, say, red blood cells. So if the average heart pumps 7,000 liters of blood a day, we can cancel out the days by saying there's 365.25 days per year, counting for the leap year. Then we can multiply that by 2 years per degree. And then finally, we can convert our liters of blood into red blood cells. So there's 5 million red blood cells per every 10 to the negative 6 liters of blood. And if we multiply everything on top, the 7,000 by 365.25 by 2 by 5 million, and divide by everything on bottom, ones, and 1 times 10 to the negative 6, then we'll see that we get 2.6 times 10 to the 19 red blood cells are pumped through your heart per degree, or per associate degree. And even though this is times 10 to the 19 and is a really huge number, this is nothing compared to 6 times 10 to the 23, because in order to pump 1 mole of red blood cells, your heart would have to pump for about 47,000 years just to pump 1 mole of red blood cells. So this number is ridiculously large. Now, the main reason we actually use this in chemistry is even though the mole is a really, really large number, the thing is that atoms are very, very small. So shown here are several different compounds measured out to be 1 mole. And typically this will be something that can fit in your hand. Oftentimes we use a mole because this is approximately the amount of chemistry we'll be, our amount of compounds we'll be using. And so one thing we can do with this is we can keep in mind that by definition, a mole is carbon 12, and that is equal to 12 grams. Now, the reason why this is important is we can relate this back to the periodic table. And if we relate this back to the periodic table, we can look at, say, natural carbon. So no longer carbon 12, but just carbon found naturally in the earth. That would be a mixture of carbon 12 and carbon 13, some other isotopes as well. But on average, they will weigh 12.01 grams. So this is the exact same value you see on your periodic table for the atomic mass. So if you found 12.01 grams of carbon in the natural Earth, that would be 1 mole of carbon. We can do the same by looking at, say, chlorine. So if we look at chlorine, we come over here to the periodic table, we find chlorine, and we could determine that for 1 mole of chlorine atoms, we need 35.45 grams of chlorine. And we can do the same thing for hydrogen. For hydrogen, it's upper left corner here, we can see that we'd have 1.008 grams of hydrogen, and that would be 1 mole of hydrogen atoms. Now, one thing we can also do with this is we can actually combine these, and we can figure out things such as the molar mass. So we can take the atomic mass of hydrogen, 1.008, and the atomic mass of chlorine, this 35.45, and we can actually go through and add these up, and we can get our molar mass of hydrochloric acid. So we just take the 1.008 grams per mole of hydrogen, add that to the 35.45 grams per mole of chlorine, and then that will leave us with a grand total of 36.458 grams per mole. And one other thing we have to kind of keep in mind here is oftentimes we need to worry about significant figures. So whenever we're adding, our significant figures for hydrogen is the last digit recorded, so that 8. So we'll go down to that 8, and then if we look at the chlorine, we'll go down to the 5. So when we're adding for significant figures, you're limited to whatever your least precise number is, or the significance of that decimal place. So in this case, we're only good down to the hundredths decimal place. So when we add everything up together, we're going to be limited to this 5 right here. And since this 8 is greater than 5, we're going to round up to have 36.46 grams. Alright, so that's how we figure out our molar mass. Now we can do the same thing with multiplication. So if we have a half of a mole of hydrochloric acid, so we only have 3.011 times 10 to 23 molecules of hydrochloric acid, then that would actually weigh 18.23 grams. So we can do math with this. If we have 2 moles, we can essentially take the molar mass and multiply it by 2. In this case, if we only have half, we can multiply it by 0.5. And so this is what the mole is. Hope y'all learned something, and I'll see you in the next video.